Hello and welcome back to Calculus 1. We are starting chapter 4, and in chapter 4 we get to apply the derivative. So in chapter 3 we learned all of these techniques of how to take derivative, and then at the end we had the method, right? The logarithmic one that kind of bypasses and kicks everything else. So now that we know how to find the derivative through basic or product or quotient or chain or implicit or logarithmic, whatever situation with trig and ln and e, we know all of that stuff, hopefully, right? It's time to apply this in chapter 4. We can use calculus, we can use derivatives, which is a slope of tangent lines, to measure change in different situations. For instance, we can measure, we can figure out where minimum and maximum of a function are, or minima and maxima if you have multiple ones. That's first lecture. We also are able to graph any function by hand if we know calculus. That's in 4.3. Optimization, which is word problems for what we're going to do now. Those are very useful. You'll see a whole bunch of the stuff. We will talk about mean value theorem, and we'll do eventually L'Hopital's rule. The last section in this chapter 4.9 will be on integration, and that is how to undo derivatives. So your exam 2 will have integrals on it, and exam 3 and the final. So integration will be in 4.9. We will learn all of the basic integrals there.
Wait, integrals will be in exam 2?
Just one section for integrals. So you will have one problem with probably A, B, and C on it, right? Because your chapter 5, 6, and 7, chapter 5 in Calc 1, chapter 6 and 7 in Calc 2 are integration. Integration done backwards. So the first lecture is on minimum and maximum. If I am to draw arbitrary function, f of x, we should all agree that there is some kind of max over here, another max over here, and some kind of a minimum right here. What is common for all of these?
Slope is 0.
Very good. Slope of the little tangent line that I drew is 0. So how do you find x value where you have min and max? You simply set derivative equal to 0. Because what is derivative? It's slope of the tangent line. Slope of the tangent line is 0 in all of these, min and max. And the lecture is over. At this point, the question is, can you solve equations? And you say, hold on, what kind of equations? And I go, polynomial one, exponential one, logarithmic ones, and trigonometric ones. Can you solve those types of equations? If you go, oh, okay, so hopefully some partial credit will help, right? So, yes, this is it. We constantly look for min and max, because what do we want? We want minimum cost. We want maximum profit. We want to see what is the maximum RPM before the engine explodes, right? That you can pull off on the engine in some sense, right? So we constantly look for min and a max. And in engineering and economics and so on, we have functions. And we have the derivative. So we can actually perform this calculation and figure out where we have these min and max values. Now, before we do any of those calculations, I have to go and say, well, do we distinguish between different versions of min and max? And the answer is yes. Because if you look at this picture, you will see two maximum values, right? But we know from the movie Highlander there could be only one, right? So, if you look at this, please note that one maximum is higher than the other maximum. Taller. Oops. So this one is taller than the other one. Also note that the function never bends up, because the function will go forever down in this particular configuration, right? Now that makes this maximum here absolute maximum. This is absolutely highest point on the entire function, right? It is the highest y value that the function attains. Now that makes the other maximum relative or local. So relative max, also known as local max, so when you are looking at this one, it's a maximum, but it's a maximum in its own neighborhood, right? If you take a look at the value of that maximum, it cuts there, so clearly there are taller points than this maximum. So we call that local maximum, right? That would be like a governor of a state in comparison to the entire United States. You're the boss in your own backyard, all right? And now we have this minimum. Would this be an absolute or a relative? What do you think? Why would you say relative? Very good. See, if you are to extend this tangent line forever in both directions, you see that these pieces of a function have lower y values. So this is definitely a relative minimum, because it's not absolutely lowest y value for the entire function. So this is going to be relative min. Now, can we have more than one absolute max? You're looking at this now, and I say yes. Cosine or sine function, it's a wave, right? So for sine, at every pi over 2 plus n pi is going to hit min or a max. But it every time hits a max and 1. So all of those are absolute max values. Because you will never attain larger value than 1 on y-axis for sine or cosine. So when you're looking at this graph, relative max over here, because there are taller points than this y value. Absolute max over here, because there are no taller y values than that y value that's there. And finally, relative minimum here, because you have function to the left and to the right plunging down to negative infinity. All of those values are lower than the y value that minimum takes. So it has to be relative. Now, if these two are to curve up, that would be absolute then. Think of x squared function, parabola, right? X squared, it has absolute maximum. So, absolute minimum. So you have absolute minimum on that. Also, you have the absolute value of x, right? Absolute value of x goes into a spike in 0, 0. Also absolute minimum. Two relatives. So if you are looking, so what Mike is showing there is a cubic function that goes below, bounces up, bounces down. A value for something like that would be x, should be x cubed minus 1 no, x minus, no. That's not x squared. Anyway. So you all you need to make sure is that for absolute max, in order for something to be, for a point to be absolute maximum, you can't have any other points to have higher y value than that one. And the same for absolute minimum. In parabola, as I mentioned, right, the x squared, you have absolute minimum because no other point will dip lower than that absolute minimum. So you can also do negative x squared, right? So absolute minimum. Okay, so now that we understand that there is a difference between absolute min, absolute max, relative min, relative max, we can go and work on the concepts that we need to compute these things. We first start with the notion of the critical point, because critical point is where you are going to have min or max occur. More can happen at that point, but for now we don't care. We just care about min and max. This is the lecture just on min or max. So, first statement is that min and max occur at the critical point. So that's the first statement that we need to know. And now the way to calculate the critical point. Critical point can be found by, number one, set f prime at x equal to 0. Solve. 2, f prime of x does not exist. At x equals a, which is the point of interest. There we go, we're done. What's the cheapest example? The cheapest example would be x squared, because we already know all of the specs for x squared. Now, the procedure that we are learning here does not require of us to know what the graph looks like at all, because this is over here the procedure that we use to compute without knowing what the graph is or where those special points are. So what do? If the function is given as x squared and they're asking for min or a max, what do? Well, first off, I know that I have to take the derivative. So f prime of x is 2x. That's always the first step, take the derivative. Now you're staring at this and you say, all right, can I make this undefined in any way? And the answer is obviously no, you can't, because it's 2x. So any number you plug in for x will work, because the domain for linear function 2x is infinite. So anything you plug in will work. So that means that the second rule, right, the f prime does not exist, doesn't hold, because we don't have an issue with the derivative. But we can use the first rule and set this equal to 0. and then solve the equation. Now, all of a sudden, you remember that I asked you always factor, 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 right? You want the factored answer. You want the product rule, factor it. You want the quotient rule, make sure it's simplified most. Because now, taking the derivative is a margin. You know, you do this in the margin of your exam so that you can actually do what is asked of you, and that is to find min or max. So now when I solve this equation, I get x equals 0. Now that is the critical number, and we can calculate its y value because we have original function. We can calculate the y value as also 0, and now that creates 0, 0 critical point. So all I did is I solved the equation to come up with x values, and then I used the x value in the original formula to come up with the y value, and now I have a critical point at 0, 0. Well, don't we know that minimum is at 0, 0? We already know that, right? This was just mathematical confirmation of something that we knew before. So here's your ABS min, absolute minimum, at 0, 0, which is the point we computed. So this is the power of this lecture. You don't have to know what the graph looks like. You don't even have to know what the function means. You can always find min and max because you take the derivative, you set equal to 0, and you're done. It's a very simple procedure. Is it always smooth? Smooth calculation. The answer is obviously no. Right? You run into the funny situation that f of x is given as 1 over x. What's the min max there? Well, you know what to do. You know what to do. Set this, find the derivative, set it equal to 0. See what happens. So to find the derivative here, we are starting with, or we are just taking the derivative. Well, what's the derivative? I'm sorry?
Negative 1 over x.
Good. Negative 1 over x squared. Now, when is this equal to 0? Because I want to, right? When is this equal to 0? And the answer is never. Very good. Because you are solving the equation 1 over x squared equals to 0. When you cross multiply, you get negative 1 equal to 0, which is not true. So now we ran into no solution. That implies no critical points. That implies no min and max. You see that? It's cool. Now let's refresh our memory of what the graph of 1 over x looks like. Do we see any min or a max on it? Obviously not. All of the corners will go to infinity. All of these function edges will go to infinity. So this is what we have. Another fun one that we need to know would be f of x equals absolute value x. Again, we already know the outcome, but let's calculate that outcome. One of the worst exams my students ever had was the one when I gave them all the answers. I was trying to make a point that the process of discovering and learning and doing the problem is actually more valuable than when you get 2.3 at the end of the problem. And I decided to, this is maybe 10 years ago, I decided to give to students the answers. So you had your answer, and I was only grading connecting the dots, right? From start of the problem until you reach that end. It was disaster. It was a massacre in a class. The average was like 27.
What?
Yeah.
Did the students just try to forcibly connect the dots?
Exactly. And when you already have the answer for problem 1, but it's not working out, right? The panic sets in, because right now you can't, right? When you don't know what the answer is, you just write something and you hope you hit the mark, right? It's like you toss a dart over there. It's like hopefully hit something, right? Back to your drink. There was the same process, right? So now, when you are looking at this situation, we already again know what the answer is, right? We know the absolute value has minimum at 0, 0, and that minimum is relative or absolute minimum. Very good. This is a 45-degree V shape. There's a spike at 0, 0, right? But now, how do we take the derivative of this monstrosity, right? I'm supposed to do this. This is where knowing mathematical definitions comes in handy. If you don't know mathematical definition, you are just doomed. So it's x for all x's bigger than 0, and it's negative x for all x's smaller than 0. And we don't really care what's happening at 0, 0. You can put equal sign on any one of these, it doesn't matter. So now, when I write the definition for absolute x, all of a sudden taking derivative is a joke, because you have a function x whose derivative is 1, and you have a function negative x whose derivative is negative 1. So 1 and negative 1 for x is x equal to 0 and x smaller than 0, right? So that's that. Now I immediately see that derivative does not exist at 0. Because, remember, derivative is a function which generates slopes. And if derivative is function, you cannot have two y values at the same x. But what does this derivative suggest? This derivative suggests 1 and negative 1. But you can't have both. Sorry. You have one or the other. So we say, and this is our previous chapter, we say that function absolute value of x is not differentiable at 0. But guess what? Not differentiable at 0 fits the criteria that I needed, right? That's the second bullet point. The derivative in this case is useless. You can't set derivative equal to 0, because you will be saying 1 equals 0 and negative 1 equals 0. That gives you nothing. But the second method to obtain the critical points in a definition there is to take a look at the points where derivative does not exist. And in this case, derivative does not exist at 0. So I'll write it: since f prime of x does not exist at x equals 0, we have a critical point at x equals 0. So now I can go and I can calculate that y is absolute value of 0, which is 0, and I got myself 0, 0 as a critical point. Now, how do we know that this 0, 0 is a minimum? Remember, we're trying to suppress that graph. right? We don't want to look at the graph of the function. We just want to do the analysis because, guys, you know what the next problem should be? ln squared of cosine x, right? Like, does that have a min or a max? You should be able to do that. Do you know what the graph looks like? You have no clue what the graph looks like of ln squared of cosine x, right? So what I have here is I have the knowledge that function is decreasing, then it hits 0, 0, and the function is increasing. How do I know that? Look at my derivative graph. Anytime the derivative graph, we learned this in chapter 3, anytime when the derivative graph is below x-axis, as it's the case for -1, which is the bottom line on our function, you see that the derivative is negative, and derivative is negative, that means the function is decreasing. Well, if I have function decreasing going into a point, which is 0, 0, and then function, so going into point 0, 0, and then after that function increasing, then it shouldn't take too much of the brain cells to say, yep, it's the ABS min. Or at least just a min, all right? So this is it. This is the scope of what we are doing in 4.1. You are either going to look for critical points through the derivative or through functions not differentiable at those particular points. Let's test them all. That's that. Now I would like to take at least 1 or 2 exercises from homework so that we all know. Let's find something. Okay, I'm accepting cookies for like 50th time. Still nothing. Ooh, the order shifted. Good thing I looked at the book. Okay. Perfect. Locating critical points. Problems 23 through 42. Right? You have over 20 problems to practice. No, 20 problems to practice. So let's pick a problem. What is a good problem? No, 31 too easy. We want either 35, 37. We want also something with trig. We want good problems. How about 35? It looks really nice. It has 1 over x and ln x. Just to make it the worst possible. All right, so let's go with the problem. Maybe we should have let's have a warm-up problem too first. Let's have a warm-up problem. So let's go with 24. Your f of x is given as 1 over 8 x cubed minus 1/2 x. Take the derivative, set it equal to 0, figure out the values, and then let me know. And no coffee.
We need to know that it's on equals -1
What happened? So let's take a look at this problem together. See you next week. So we have the derivative, which is f prime of x is equal to 3/8 x squared minus 1/2. We set this equal to 0. We're good? And then I multiply both sides by 8 to have 3x squared equal to 4. Because when you multiply by 8, 1 times 8 is 8, divided by 2 is 4. Move that to the other side. X squared is equal to 4/3. When you square root both sides, you get x equals plus minus 2 over root 3. And since we don't like root 3 in denominator, we rationalize. And my critical points are plus minus 2 root 3 over 3. So I have two critical points. Well, these are critical numbers because it's just a x value. I need to calculate the y value, which is actually easy because we get to plug this in into the original function and work it out. So we can figure out for x equals 2 square root of 3 over 3 what the f of 2 square root of 3 over 3 is by plugging it in. So that's 1 over 8 times 2 root 3 over 3 cubed minus 1/2 times 2 root 3 over 3. Just need to do some calculations here. So at least 2's will cancel. And then 2 and 8, because 2 cubed is 8. So that cancels. So the whole thing simplifies. This is y equals f of 2 root 3 over 3. What do we have left? 3 and 3 would cancel, so we have a root 3 minus root 3 over 3, which is 2 root 3 over 3. So I have my critical point, 2 root 3 over 3 and 2 root 3 over 3. And now you will have to calculate the other one as well. Now, how do I know if this is a min or a max? Like, how do I know that?
Fine.
Well, what we can do, well, can't do signs because you can have, you mean sine of the y value, right? Well, you can have a maximum that here, right? This maximum is, right?
Well, I mean, if one's negative and the other's positive, the positive is probably going to be the max.
As soon as you say that, this minimum here is higher than this maximum here. See? None of those unfortunately work. Now, but what does work is realizing, well, first off, we are going to have a different, wait, they changed the order of sections, so I need to see which section this is going to be in. I think 4.3. So in section 4.3, we are going to learn, section 4.3, we are going to learn the cool method to do this. Right now, we just have to do long, annoying calculation. You see, you have a point that has x and a y coordinate. So let me see what this approximately is when we do the in the calculator. So 2 divided by 3, 2 divided by 3 times the square root of 3 is about 1.15. So this is about 1.15 comma 1.15. This is what you have. So all I need to do is to calculate the y value for 1. Why would I calculate y value for 1? Because y value at 1 is either going to be higher or lower than 1.15. That makes sense? So if you think about it, every maximum is on top of the hump, every minimum is on the bottom, right? Now observe what happens to the value that is close by. You see that? You have different elevation on y-axis. So if you pick a close point, you will come up with one of the two configurations that you see on the picture. When you move a little bit to the left or a little bit to the right, just a little bit, and we are moving only 15 cents to the left to get to number 1. The y value you compute in the original function will be either lower or higher than this y value. If it's higher, it's a minimum. If it's lower, it's a maximum. It's a very simple concept. So, I'm just going to compute f of 1. And the f of 1 for our problem is 1 over 8 minus 1/2. So times 4, negative 3/8. That's lower. So this is a max. It's a max value because, again, we calculated, so we have our 1.15 x value, then I went and I calculated what's the y value for 1, which is a little bit to the left. What I came up with, it was smaller than the y value here. This is a really annoying way to figure out what min or max are, but it's the way that always works if you're willing to compute function values, right? We are going to focus on more, algebra methods than this. So you can always figure out. And now the other one, you do the same thing. You go, you compute, you figure out, and you will get minimum, and that's that. One more example. But I want this one to be, let's go with 35 because it has 1 over x and ln x. Why is it stuck now? Did you start an update or something? That works. Pen works. Software probably doesn't work. Well, we'll do this one problem 35 off stream, and then I'll just do the, because I have to restart.
It just worked. Oh,
No, I can't scroll to, for whatever reason, I can't scroll to get more paper on the bottom. Like the pen works, the menu works, I can't shut off the software using pen or a finger, and I can't scroll up and down. So all I can do here is I can just write what the function is, and then we'll do this off stream when I restart. So it's 1 over x plus ln x. Find critical points, and then, you know, using this middle school calculation, a little bit to the left, a little bit to the right, figure out what we have. So, yep, that's that. Now let's see if I can restart this. Well, oh, I didn't restart. I just didn't restart yet. I'm trying to see if this will work, but it doesn't.